Good day everyone, my name is Joshua L.G. Paharon and I am a BS IT student from the section 2A. Today I will teach you about QuickSort, or we will talk about it, and I will explain to you what is QuickSort. I am going to read this paragraph or a bunch of paragraphs and give an explanation afterwards. So first, what is QuickSort, or what is it? QuickSort. QuickSort works by obtaining a pivot and partitioning the array around it, or the bigger elements on one side and smaller elements on the other side, until everything is sorted. The ideal pivot is the median of the array, since it will partition the array evenly, but getting the median of an unsorted array linear time to compute. Hence, a pivot is typically obtained by taking the median value of the first, middle, and last elements in the partition. This sort is a recursive one and uses the divide and conquer methodology to break the quadratic complexity barrier and get the time complexity down to O n log 2n. However, with a pivot that partitions everything on one side, the time complexity is worst case 0 and 2. So I will first explain this slide. Now let's talk about the ideal pivot, or the pivot selection. The ideal pivot is indeed the median of the array. It will lead to the most balanced partition. It ensures that the sub-arrays are roughly equal in size, leading to the best time complexity. But how do we find the median? First, finding the median of an unsorted array in linear time, or ON, can be challenging. The practical pivot selection is that the common approach for it is taking the median of the first, middle, and last elements of the partition. It is a good compromise. It's fast to calculate and often gives a distant pivot that avoids extreme imbalances. Now, for its time complexity, the average case is the O n log 2n. The QuickSort achieves its efficiency because of divide and conquer strategy. When the pivots are chosen reasonably well, like the median of 3 approach, the array is partitioned into roughly equal halves at each step. This leads to a logarithmic number of levels of recursion, or log 2n, since each level involves processing n elements. The overall time complexity is O n log 2n. The worst case is that it occurs when the pivot constantly divides the array extremely unevenly. Imagine the pivot always being the smallest or the largest element. In this scenario, one subarray is empty and the other contains almost all the elements. This leads to a linear number of level of recursion, or n. Since each level involves processing n elements, the overall time complexity becomes O n powered by 2. Now, let's talk about why this QuickSort works. Or when it is divide and conquer, using divide and conquer, the QuickSort, remember, it breaks the problems of sort by sorting into smaller, more manageable sub-problems, or the partitions. This is the essence of the divide and conquer, the partitions. the divide and conquer. Now, its recursive nature. Now, the algorithm is recursive. It keeps calling itself on the smaller subarray until the entire array is sorted. The breaking quadratic barrier. Now, the average case time complexity of O n log 2 n is significantly better than the quadratic complexity of O n powered by 2 of some other simpler sorting algorithms like bubble sort or insertion sort. So QuickSort's efficiency really relies on choosing good pivots to create a balanced partitions. The median of the three approach is a practical way to select pivots that often avoid extreme imbalances. The worst case time complexity of O n powered by 2 is a concern, but it's relatively uncommon. So QuickSort average complexity of O n log n makes it powerful and widely used sorting algorithm. Now let's go to the next slide. So this is the QuickSort code or its description. Let's talk about the QuickSort code. I'm sorry. Now its description. The following code implements the insertion sort algorithm. The outer for loop iterates over the array indices, and the inner for loop moves the unsorted items into the sorted sublist on the left side of the array. The time complexity. This is the time complexity of the QuickSort. It is O n log n on average and O n squared for worst case scenario. And this is the worst case scenario for time complexity is the O n powered by 2 and the average one is O n log 2 n. And its space complexity is O log 2n. And the QuickSort code is best for larger data sets. So before we proceed to the next one, let's talk about time and space complexity. The time complexity with its average case is the O n log n is the most common and often based scenario of QuickSort or this one. The time it takes to sort the array grows roughly proportional to the number of elements, which is n. The element is n, multiplied by the logarithm of the number of elements, which is log n. This means QuickSort is very efficient for data sets. For its worst case scenario, which is the O n squared, this happens when the pivot is constantly chosen poorly, meaning that the time to sort grows proportionally to the square of the number of elements, which is n. This makes QuickSort less efficient in these rare cases. The next one is space complexity. So, the average space complexity, the O log n, this represents the amount of extra memory used by the algorithm, meaning the space used grows logarithmically with the number of elements. This is because of the recursive calls, which create a call stack that is roughly proportional to the depth of the recursion, which is log n. Its worst case scenario, which it has, is O n. It's like this but without 2. O n. This occurs in rare scenarios where the recursion goes very deep, potentially using extra memory proportional to the number of elements. So, let me show you something first. So, let's talk about the sign. First, let's do this. The O, and then this, and N. First, I will type the signs, okay? The next one is the O, N, log N, after that is the O, oh no, first make it big, N, powered by 2, and parenthesis again, then O log N. After that, lastly is O 1. So I will explain the meaning of each one. So first, let's talk about ON. It means the linear time complexity. The time grows proportionally to the number of elements. That is what the ON means. For ON log N, it means the logarithmic time complexity. The time grows slightly faster than linear but still very efficiently. For ON powered by 2, it is the quadratic time complexity. The timing gets much faster than linear, becoming let me count again. Sorry. The ON squared is the quadratic time complexity. The time grows much faster than linear, becoming significant for larger data sets. For O log N, it is the logarithmic space complexity. Remember, O log N, ON log N is logarithmic time complexity, and O log N is logarithmic space complexity. The time used grows slowly with the input size. That is what it means. For O1, it means constant space complexity. The space used is independent of the input size. Now let's talk about the time and space complexity of the QuickSort code. Now, remember that the time complexity, the average case is ON log 2N. N, remember, represents the number of elements in the array that we're sorting. Log 2N, or let me show you. The log 2N, and like this, but the 2 is smaller and at the bottom of G in a little bit. It means that this is the base -2 logarithmic of N. It tells us how many times we can divide N by 2 before we get to 1. It's a way for measuring how many levels of recursion are needed in QuickSort. For example, if we have 16 elements, like n's 16 log 2 16 equals 4, this means we can divide 16 by 2. 4 times 16 is 16 to 8 to 4 to 1. 2 to 1. Let me show you. So like this. So like we have 16 elements, which is n16, and is log 2 16 equals log 2 16 equals 4. This means we can divide it 16 by 2 4 times. Like, see, it's 16 to 8 to 4 to 1. It means that in the average case, QuickSort performs roughly n operation for each level of recursion, since there are about log 2 n levels. The total time complexity complexity is roughly n times log 2n. This makes QuickSort very efficient for large database. Now, let's go for the worst case scenario. The worst case scenario is this one, remember? This one, the n2. It means the time to sort goes proportionally to the square of the number of elements. This happens when the pivot selection is constantly bad, leading to very unbalanced partitions. Now, let's move. That is for the time complexity. Now let us move to the space complexity. The space complexity. The log 2n, again, this refers to the base 2 logarithm of n. It means that the amount of extra memory used by QuickSort grows roughly proportional to the number of levels of recursion, which is log 2n. This is because of the call stack used for the recursive calls. So, why log 2n? It is because of the divide and conquer. QuickSort works by dividing the program in half of each step, roughly. This repeated halving is what leads to the logarithmic behavior, and it's the call stack. Each recursive call in QuickSort adds a frame to the function call stack. The call stack to the depth of this stack is related to the number of times we can divide the array in half, which is log 2n. So, log 2n in QuickSort time and space complexity reflects the algorithm's divide and conquer nature, where the problem is repeatedly halved. The average time complexity of O and log 2n makes the QuickSort efficient for larger datasets. In the worst case, time complexity of O and 2 is less common, but it highlights that bad pivot choices can significantly impact the performance. The space complexity of the O log 2n indicates that QuickSort uses extra memory that grows slowly with the input size. So here is another paragraph, the QuickSort time and space complexity. The time complexity of O and log on average of O, and for worst case scenario, space complexity of O log 2n. One downside about the QuickSort algorithm is that it could potentially be a O n squared, like what I told you about a while ago. If a bad pivot is always picked, a bad pivot is one that it does not partition the array evenly. The ideal pivot is the median element of the array. In addition, a quicksort algorithm takes a bigger space complexity of O leg 2n compared to other sorting algorithms because of the call stack in recursion. Use a quicksort algorithm when the average performance should be optimal. This has to do with the fact that quicksort works better for RAM cake. So, as we mentioned, the worst case scenario for quicksort that we mentioned happens when the bad pivots are constantly chosen. This leads to extremely unbalanced partition. For example, if the pivot is always the smallest element, the left subarray is empty, and the right subarray contains all the remaining sub-elements. This results in a linear number of recursive levels n, leading to O(n) squared time complexity. So we will talk about the median of three approach. The median of three approach is by picking the median of the first, middle, and last element. It is a common strategy to avoid constantly getting or finding bad pivots. And there's also the random pivot selection. It is the choosing a random pivot element can also help us reduce the chance of constantly bad pivots. These are the mitigations. So now let's go to the space complexity. So the recursive call stack, the O leg 2n, is each recursive call adds a frame to the stack, and the depth of the stack is roughly log 2n in the average case. While O log 2n space complexity is generally considered efficient, some sorting algorithms like insertion sort and selection sort have a constant space complexity of O1, meaning they use a fixed amount of extra money regardless of the input size. So let's talk about when to use QuickSort. The average performance is that QuickSort is an excellent choice when we need optimal average case performance. The O log 2 and average time complexity makes it very efficient for large datasets. So let's talk about the RAM cake optimization. QuickSort performance is often enhanced by the way it interacts with the RAM cake. It lends to access data in the more localized way, which can improve speed. Now let's talk about its worst case concern. The potential for O(n) to time complexity is a downside, but it's relatively uncommon with good pivot selection strategy and its space consideration. While QuickSort's space complexity is generally efficient, it is important to be aware of the potential for extra memory usage due to the recursive call stack, especially when dealing with large data sets. So, QuickSort, it is a very powerful algorithm with excellent average case performance, but it is very important we must be aware of the potential for the worst case time complexity and the extra space used due to recursion. It is a good choice that the QuickSort when we need optimal average performance and can tolerate a slightly higher space complexity. So now, we're done with this one. Let's proceed to the code. I will show you a code and I will explain it to you how it works. Okay? This is the code. And when we run it, a bit. Oh, this is the unsorted array is the 8721,096, and the sorted array is the 012687 by order. So I will explain this code to you. So remember, QuickSort is a sorting algorithm that uses divide and conquer strategy. It means that it breaks down the problem of sorting a large array into smaller, more manageable subproblems. So for example, let's imagine that we have a pile of unsorted books. What QuickSort would do is that it will pick a book, which is the pivot, picking the book, and divide the pile into two smaller piles. Book smaller than the chosen book go to one side, the left, and the books larger than the chosen book go on the other, which is the right. It will repeat this process for each of the smaller pile until all the piles have only one book, which it is already sorted. So finally, combining the sorted piles to get the final sorted pile of books. So we will now break down the code. So we will talk about this one first. What this is. It is the QuickSort R low high. This is the main sorting function. This is the function is responsible for the entire sorting process. R means this is the array that needs to be sorted. Low, the starting index of the subarray we're currently working on, and high, the ending index of the subarray we're currently working on. So the next one is, what is this? If low high. This condition, the if low high, checks if the subarray has more than one element. If it does, we need to sort it. So we will proceed to let pi equals partition r low high. This line calls the partition function, which partitions the subarray around a pivot element and returns the index pi where the pivot is placed. The next is QuickSort r low pi minus 1. So this recursively calls QuickSort on the subarray to the left of the pivot from low to pi minus 1. The next one is the QuickSort r pi plus 1 high. This line recursively calls QuickSort on the subarray to the right of the pivot from pi plus 1 to high. Now the next is the partition function, the r low high. This is the partition function. This function is the heart of our QuickSort. This is the one responsible dividing the array into two parts based on a pivot element. The next one is the let pivot equals r high. This line selects the last element of the subarray as the pivot. So the pivot in our array in this function is the last one. The next one is let I equals low minus 1. This initializes the counter I to keep track of the index of the last element smaller than the pivot. The next line, for let j equals low, j is lesser than high, semicolon, j plus plus. This line is a loop which iterates through the subarray from low to high minus 1, excluding the pivot. So the next is if rj equals pivot, this condition checks if the current element or the rj is less than or equal to the pivot. So the next is I plus plus r this whole one, the I plus plus semicolon r, this one ri and rj equals rj ri. This line is less than or equal to the pivot. Wait, let me explain it again. So I plus plus is r I and rj equals to rj and ri if rj is less than or equal to the pivot. It's swapped with ri plus 1 to move to the left side of the pivot. The counter I is then incremented. Oh, this is the whole code meaning. The next one is ri plus 1, comma, r high equals to r high, comma, ri plus 1. After the loop, the pivot is swapped with ri plus 1 to place it in its final position. So, let's start. The next one is return I plus 1. It is to place in its final. This is the function. This returns the index I plus 1, which is the final position of the pivot after partitioning, which is the one above. So, the example usage, this one. So, let data equals 8721096. This creates an array of numbers to be sorted. The next one is console log, unsorted array data. It prints the unsorted data. And the next one is QuickSort data, 0, data dot length -1. This calls the QuickSort function to the sort array. And the console log, the final one, is the sorted array data. It prints the data array, which is this one. This is the result. Remember that the pivot in our code that is given here is the last element of the array. As remember the function partition r low high is the function responsible for partitioning the array around the pivot. So the let pivot r high, which is this one is line specifically selects the element at the high index, which is the last element of the pivot. So here's how it worked. The partition function initializes I to low -1. It iterates through the array from low to high -1, excluding the pivot, as I said a while ago. For each element rj that is less than or equal to the pivot, it swaps ri with ri plus 1 and increments I. Finally, it swaps the pivot, which is at r high, with ri plus 1 to place pivot in its final position. So in the code here, the pivot is always the last element. But remember, this is only one of the ways to choose a pivot. There are other strategies, like the median of 3 approach. So I will give you an extra info about pivots. So in QuickSort, the pivot is a crucial element that helps divide the array into 2 sub-arrays. The goal is to place the pivot in its correct sorted position, ensuring all elements smaller than the pivot are to its left and all larger elements are to its right. The statement pivot is typically obtained by taking the median value of the first, middle, and last element in the The partition refers to a common strategy for choosing the pivot, which is the median of three partitioning, the one that I told you about. The pivot, the first, middle, and last elements, the finding the median value, it is the median of three partitioning. Here's how it works, the median of three partitioning. It selects three elements, it is the first, middle, and last elements of the partition that we're working with. It finds the median, it calculates the median, and finds the middle value of the three elements. It uses the median as the pivot. The median value becomes our pivot for the current partition. Why should we use median of three partitioning, or why? It's because it reduces the bias. Choosing the pivot randomly or always picking the first element can lead to worst case scenarios where QuickSort becomes inefficient, or the O(n squared). Median of 3 helps mitigate this by selecting a more representative pivot. And this way, the median of 3 partitioning improves in performance. A well-chosen pivot generally leads to more balanced partition, resulting in faster sorting. So, this is an example. The 7521998. First, we select the 3 element, which is the 7, the 7. Next is 1, assuming which is the middle part of our array. And the last one is 8. So let us find the median of the 7, 1, 8. And as we can see, it is 7. Then we use the median as the pivot, which is 7. So our 7 becomes the pivot for this pattern. So, here's an important thing. While median of 3 is common, other pivot selection strategies exist, like choosing a random element or always picking the first element. The choice of pivot selection can impact the efficiency of QuickSort. Okay? So, regarding of picking the pivot or the strategies, here is some strategies. The first one is the first element. And how it works is the simplest approach is we pick the first element of the partition as the pivot. Its pros is that it is easy to element, but the cons, it can lead to worst case scenarios if the input array is already sorted or nearly sorted. In this case, the pivot will always be the smallest or largest element, resulting in highly unbalanced partitions and ON2 runtime. The next one is last element. How it works? It is similar to the first element, but we choose the last element of the first as the pivot, like what we used in the code, in this code. It is relatively simple, but the cons is accessible to the same worst case scenario in the first element strategy. The third one is random element. How it works? It selects a random element from the partition as the pivot. Its pros, it helps avoid worst case scenarios by reducing bias. Its cons, it requires additional randomness generation, which adds a slight overhead. The fourth one is the median of 3, which we talked about. As explained earlier, it calculates the median of the first, middle, and the last element of the partition. The median becomes the pivot. Its pros, it's often a good compromise between simplicity and reducing worst-case scenarios. Its con, it's slightly more complex than the first and last element strategy. So, the example that I have given you, the code, is a last element pivot. It used. Now, the next one is the horse partition scheme. So the horse partition scheme. How it works is this scheme uses 2 pointers, one starting from the left and the other from the right. The pointers move inward, swapping elements as they encounter elements that are out of place. Its pros, it can be more efficient than other partition schemes in some cases, but the cons is it is more complex to implement. So, about choosing the best strategy, median of the three is a wildly used and generally effective strategy. It offers a good balance between simplicity and reducing the likelihood of worst case scenarios. The next one is random element is another solid option for avoiding bias. If we are concerned about performance and have larger data set, we should consider exploring horse partition scheme, but we must be prepared for increased implementation and complexity. Implementation complexity. So we have to remember the best pivot selection strategy will depend on our specific dataset and performance requirements. We should experiment with different strategies to find to find what works best for us to use. I will give another extra, which is that, for example, we are looking for the median between three chosen numbers, like the median of the three. Remember, we choose three and we find the median of the three. Firstly, we will have to sort the numbers. It will arrange the three chosen numbers in ascending order from smallest to largest. It will identify the middle number. The middle number in this sorted sequence is the median. For example, this is the example. Let's say our three chosen numbers are 5, 1, and 8. We sort it to 1. We sort it to 1, 5, 8. The median number is 5, so the median is 5. The middle number is 5, so it is the median. See? This is the code. This is an extra. So, in the sorting number, the numbers is essential for finding the median. The middle number, the median is the middle value, so it's the second element in the sorted array. Like we chose the three numbers and arrange them like the example here in the 7, 1, like what we chose this one in the given, like for example this one, the 7, 5, 2, 1, 9, 8. The three chosen is the 7, 1, 8. 7, 1, 8. So what we did for the median is that it will choose the median by putting in a range. It's 1, 7, 8. So the middle one is 7, so it is the median. So here's another one regarding it, the median. If it is even number of elements, if we had an even number of elements, the median would be the average of the two middle numbers after sorting. So that is all that I could teach you today, and thank you for listening to me, dear viewers. Thank you for listening to me. I am Joshua Lyle G. Paharon, a BSIT student from the Section 2A. I hope my teaching can help you, or what we have talked here in this video will help you learn more, understand more about QuickSort. About QuickSort and the ways we could, and the extra knowledge, extra lesson that I give you regarding pivots. I hope my video has helped you, And thank you for watching the video. God bless you all. May you have a great and wonderful year, day, your entire lives. God bless.